Myelin is an extremely important material in the human body, so let's take a moment to understand how it works in greater detail. As we discussed, while giant axons allow fast signal propagation, they aren't always a particularly practical solution to the problem of increasing conduction velocity. Giant axons enable fast action potential propagation by lowering axial resistance. But we also said earlier that we could get faster propagation by lowering the membrane capacitance, and that's exactly what myelin does. Assuming a parallel plate capacitor geometry for simplicity, we see that the capacitance is proportional to the dielectric constant of the insulating material and the distance between the conductive surfaces. In the passive membrane properties section, we mentioned that the lipid bilayer is actually a pretty good dielectric material. There's realistically not much more we can do with material properties of the membrane to lower its capacitance. But we can increase its thickness, and in doing so, we increase the separation between the two conductors. And as we can see from the equation, increasing this distance lowers the capacitance. Nature does this in a clever way. It doesn't physically increase the thickness of the membrane per se. Instead, a supporting cell wraps a sheath of myelin around and around the axon, multiple times to make the dielectric thicker. It's sort of like wrapping a roll of electrical tape around a wire. Even when wrapped many times around, it's still much smaller than the giant axons needed for fast conductions in squids and other invertebrates. Layering on myelin changes the membrane potential in two ways. It increases the membrane resistance, and it decreases the membrane capacitance. The membrane resistance increases because any leakage channels that would have previously allowed the flow of ions through the membrane are now blocked by the myelin. Excluding these channels stops current from flowing through the membrane, and the result is an increased membrane resistance. This results in a longer length constant because more current is able to flow down the axon, with less of it being diverted along unproductive paths through the membrane. Since more current flows down the axon, the membrane potential changes more over longer distances. At the same time, decreasing the capacitance reduces the time constant of the membrane, speeding up changes in membrane potential. This allows changes in membrane potential to be transmitted more rapidly down the axon,